Welcome to this college algebra video on inverse functions.
Before we talk about inverse functions, let's try a little warm-up problem here. See if you can do the composition of functions f composed with g and g composed with f. I'll pause for a second and then we'll continue. All right, hopefully you have finished that up now, and I'll go ahead and show you the solutions here. First, f composed with g. Remember, that means that f, the function f, is going to swallow up the function g. So everywhere I see x in the function f, I'm going to replace it with the function g. All right, now I'm going to simplify a little bit. 5 times this fraction with a denominator of 5. We'll see that the 5's will cancel. And this will leave us with x plus 4. I've taken care of that parentheses by multiplication, so no need for parentheses anymore. X plus 4 minus 4, well, that's just equal to x. So f composed with g left us with a result of just the function y equals x. Let's see what g composed with f is. So I'm going to write g of x, and everywhere I see x, I'm going to replace it with the expression 5x minus 4. So I take 5x minus 4, where we see this x, then we have plus 4, and it's all divided by 5. And we'll simplify a little bit. Well, minus 4 and plus 4 adds up to 0. So now we have 5x over 5. And when the 5's cancel out, again, we have wound up with the result of just the function x. So g composed with f was equal to x. F composed with g and g composed with f, the result both times was the function y equals x. We'll see why this particular arrangement is kind of special in just a little while. Well, let's move on here to a few definitions, a few basic definitions that are mentioned in Chapter 5, Section 3, is the definition of increasing and the definition of decreasing, as well as one more definition. A function is increasing on an interval if, when x1 is less than x2, f of x1 is less than f of x2. That means when an x value is less than another x value, the function value that goes with that first is less than the function value that goes with the second. So another way of thinking of this is, as my x's get bigger, my function values will get bigger. And that's what it means to be an increasing part of a function. Decreasing on an interval, well, now for x1 less than x2, f of x1 will be greater than f of x2. That is, for a smaller x, we'll get actually a larger function value. And as the x values get larger, our function values will get smaller. That's the idea of decreasing. We'll see that some functions are always increasing, some functions are always decreasing. Other functions have certain intervals where they're increasing and other intervals where they're decreasing. The last type of section we'll talk about here is a constant. And constant on an interval means that f of x1 equals f of x2. That is, function values are equal no matter what x I decide to put as my input. So here's an example of a function. Let's look for where it is increasing and where it is decreasing. We can see that at the beginning here, as my x values increase, my y values also increase. So if x1 is less than x2, f of x1 is below f of x2. That meets the definition of an increasing function. And so for this interval, this function is increasing. Now, as soon as we get past about 1.5 or 2, this function begins to decrease. That is, as x1 is less than x2, the function value at x1 is higher than the function value at x2. So Here the function is decreasing. And then from about, let's see, looks like about x equals 6 on through maybe infinity, we have the function increasing again. So x1 is less than x2, and the function valued x1 is also less than the function valued x2. So from about the x value x equals 6 on up to infinity, this function is increasing. So we see one interval where the function is increasing, an interval where the function is decreasing, and an interval where the function is increasing again. On the next picture, we're going to see an example of a function which is constant. Notice that no matter what x values I choose, f of x1 is equal to f of x2. They have the same function value all the way across here. And a constant function will basically look like just a horizontal line. Next definitions that we want to talk about are one-to-one functions. A one-to-one function is a function in which each output can be traced back to a unique input. We'll look at some visual examples and some other ways to see one-to-one functions. But here's the essence of a one-to-one function. Every y value in the range corresponds to only one x value in its domain. Previously, when we've talked about functions, we have seen some functions where you can get the same y value from two different x values. Well, that is not allowed in a one-to-one function. I cannot get the same answer twice. If a graph of a relation passes the vertical line test, then it's a function. You remember the vertical line test from the last chapter, and we'll show you that vertical line test again. Remember, that's just the basic test of if something is a function. Well, if it also passes the horizontal line test, then that function can be said to be one-to-one. And a one-to-one function, we're going to see, is a very important condition for having inverse functions. So here's an example of using the horizontal line test. The first thing we're going to do is we're going to illustrate the vertical line test again. Remember, we see a graph and we want to know whether this thing is a function. So we sweep a vertical line through it. If that vertical line never touches the graph in more than one place, then we say, yes, that graph is a function. And in this case, this passed the vertical line test. Now we're going to perform the horizontal line test on that same graph. I'm going to run that horizontal line through the graph, and if it ever touches the graph in more than one place at a time, it will fail the horizontal line test. So it starts going up, and already we've seen places where it not only touches the graph twice, but 3 times at the same y value. So that is not a one-to-one function. It failed the horizontal line test. Here's another example. Well, this one fails the vertical line test. So it's not even a function, much less a one-to-one function. It also fails the horizontal line test. So not a function, definitely not one-to-one. Here's another graph. Let's see if it passes the vertical line test. It seems to pass the vertical line test, so it is a function. Let's see if it passes the horizontal line test. As the horizontal line starts to move up, we pretty quickly run into a place where it touches 2 places on the graph at once. This is not a one-to-one function. It's just a function, not one-to-one. Here's another example. This graph passes the vertical line test. This graph also passes the horizontal line test. There's no place where the graph touches that horizontal line in more than one place. So this would be considered a one-to-one function. Here's another graph. We'll run the vertical line test through, and it passes. This is a function. We'll run the horizontal line test. It also passes the horizontal line test. So not only is this a function, it is a one-to-one function. And finally, here's another graph. This passes the vertical line test, but it fails the horizontal line test. So this is a function, but not a one-to-one function. So to summarize, after performing the vertical line test, we saw that all but one of these was a function. Only the middle top was not a function. Every one of these, except for the middle top, passed the vertical line test. Now we've performed the horizontal line test, and we saw that the first three functions failed the horizontal line test, so they were not one-to-one. The fourth and fifth functions actually passed the horizontal line test, so they are one-to-one. The last function did not pass the horizontal line test, so it was not one-to-one. So now let's talk about the inverse of a function. This is where section 5.3 was heading. This is the big topic of section 5.3. First, notation. The inverse of a one-to-one function f is written as f inverse. That's how we'll read this, f inverse. This is not a -1 power. Don't read it as f to the negative first power. Negative powers put things in the denominator. This is not what this means. We'll see later how to take a function and find its inverse and write the formula for the inverse. But thing to understand, it does not mean put the function in the denominator. That's usually what a negative power means. Unfortunately, the notations look very much the same. But this is not a negative power. Read it as f inverse. Now, it's key to understand that only one-to-one functions can have an inverse. That is, if a function is not one-to-one, then it does not have an inverse function. The inverse of a function, what is it exactly? It's a new function which traces the outputs of f back to their inputs. And we'll see that illustrated in our machine illustration in just a second. Another key feature of an inverse function is that for any ordered pair xy, that is a point on the function f, the reverse pair yx is a point on the function in f inverse. Here's another key fact about functions and inverses. The composition of f and f inverse always equals x. So you may remember from our warm-up, we composed two functions and the result was x. Well, the reason the result was x was because the functions that I gave you on that warm-up were inverses of each other. And here's that written in notation here. F composed with f inverse results in x. And f inverse composed with f also results in x. So interesting thing is it doesn't matter the order we do the composition. Both of them will result in x, the function y equals x. Well, let's go back to the machine analogy that we've used for functions before, and we're going to try to answer this little question. If f of a equals b, then what does f inverse of b equal? So remember, this is an input of a that gives an output of b. In the machine illustration here, we've seen, say, an input of 5 that might give us an output of 36. So some kind of processing happens to that 5, it goes through some kind of a formula, and the output is 36. Now the question is, what is f inverse of 36? Is there some way of predicting what the f inverse function will do to 36? Well, let's create a new machine and suppose this is f inverse. Well, f inverse takes its inputs and traces them back to where they came from in the original function. So an answer of 36 came from an input of 5. That means f inverse of 36 will lead us back to 5. So if f of a equals b, then f inverse of b will equal a. So this is what we mean by a function tracing an output back to its input. Some more examples. If the input was 8 and my original function produces an output of 48, when I put 48 into the inverse function, it's going to produce an output of 8. If our input is -10 and the original function leads that to a negative 24 output. Then a negative 24 input into F inverse is going to lead to an output of negative 10. So the F inverse function has a way of tracing outputs back to the inputs they came from. All right, let's use composition to verify that this function is the inverse, or each of these functions is the inverse of the other. So this is basically what we did in the warm-up. We want to compose F and G in both orders. We want to do F composed with G. We also want to do G composed with F. So I'll do this by hand here. First, let's write F composed with G. And remember, this is the little open circle is the notation for composed. That means F gets to eat the function G. So first, we're going to put the function G as the input of F. So when x gets squared, that actually means the square root of x plus 5 gets squared. And the rest of the function F is to subtract 5. When we simplify that, that is square cancels out the square root, so x plus 5 minus 5. And that simplified is equal to x. So F composed with G produces the output of x. So we're halfway to verifying that these are inverses of each other. We also need to do G composed with F. So I'm going to let G swallow up F. That is in the G function. Everywhere I see x, I'm going to replace it with f of x. So instead of writing x, I'll write x squared minus 5. And then also in g of x, we have plus 5. And let's simplify that. The 5 and the negative 5 cancel out. We have the square root of x squared. And as long as x is a positive number, square root and square cancel each other out, and we get a value of x. So f composed with g gave us a result of x. G composed with f gave us a result of x. That confirms that f and g are inverses of each other. So yes, f and g are inverses of each other. Let's also examine what the graphs of f and g will look like. And let's see, notice this is f of x for x's greater than or equal to 0. I wonder why that particular condition was put on there. Well, let's take a look at the function x squared minus 5. And I'm going to look at this on a square window. There's the function x squared minus 5. It definitely passes the vertical line test, but notice this would fail the horizontal line test. So how does this even have an inverse? Well, remember the condition was x squared minus 5 for x is greater than or equal to 0. Well, I can get the graphing calculator to only graph that part. All I have to do is put a little condition in here. X's, and I hit the test button, second math, greater than or equal to 0. And with that little condition in here, it will draw the graph only for x is greater than or equal to 0. Now notice this new graph is a one-to-one function. It passes the vertical line test. It also passes the horizontal line test. And now let's compare the graph of that to the graph of square root of x plus 5. And we'll see the red graph and the blue graph definitely have sort of a relationship here. There's almost a mirror image of each other. In fact, they are a mirror image over the line y equals x. And that is always true for graphs of inverse functions. The inverse function will always be a reflection of the original function over the line y equals x. So one of the key things that you'll be asked to do in this assignment is actually find the inverse of a function. And there are a number of ways to do it. On a graph, you would simply reflect the graph over the diagonal line y equals x. So if you have a drawing of a function, you could draw the inverse of the function. Just do that mirror image over the line y equals x. Reverse the points x, y into points y comma x. So reverse the coordinates of all the points and you'll have that new function, which is the inverse. The more difficult kind of problem is if you're given a formula. So if you're given a formula, f of x equals some kind of a function here, some formula for how to compute f of x, here's the process for finding the inverse. I'll give you some steps and then we'll do some examples. The steps are, first, replace the f of x symbol with y. So this will look like y equals some kind of formula. Step 2, interchange x and y. Step 3, solve for y. This is probably where most of the work is going to be involved. And step 4, replace the y symbol with f inverse of x. So let's see I've got several examples of this, and hopefully by following these examples, you'll be able to do the same process on the assignment. So here's the first of 4 examples. In each case, the instructions are going to be find the inverse and state the domain of the inverse function. So we'll follow the process that I outlined on the last page, and then we'll talk about the domain. First step in the process is change f of x to be a y. So I'll write this as y equals 4x minus 5. Step 2 is to interchange x and y. So where I see y, I write x. Where I see x, I write y. The next step is where most of the work is involved. This is solving this equation for y. So I want to isolate y, get it by itself. First, I might need to get rid of this 5, so add 5 to both sides. X plus 5 is equal to 4y. Y is still not by itself, so I need to divide both sides by 4 to be able to cancel out that 4. Now, for our last step, instead of writing y, we're going to write the notation that f inverse of x is equal to x plus 5 all divided by 4. Now, as I look at this function, I don't see any x's in the denominator. I don't see any square roots that we'd have to worry about keeping positive. So the domain of this function is all real numbers. And what we've done is we've now found the function that will take any output from f of x and trace it back to its original input. Let's try another example. So our new example, f of x equals 3/4 x plus 3/5. This is typical linear function here in the mx plus b form. Let's find the inverse of this function, and we'll follow the same process. First, replace f of x with y. Y is equal to 3/4 x plus 3/5. Next step is to interchange x and y. So where I see y, I write x. Where I see x, I write y. Oops. Now is where the work starts. I need to isolate this y, solve this equation for y. Well, one of our good techniques we know for fractions is to multiply by the LCD. That will clear these fractions. Multiply by, and the lowest common denominator for a 4 and a 5 is the number 20. 20 times x is 20x. 20 times 3/4 y is 15y, because 15 is 3/4 of 20. 3/5 times 20 is 12, because 3/5 times 20 is 12. Now I can more clearly isolate the y. I can subtract 12 from both sides. We have 20x minus 12 equals 15y. And as a last step, I can divide both sides by 15. And again, when I write my final answer, I'm going to do that final step of, instead of writing a y, I'm going to replace the y with the notation f inverse. F inverse of x is equal to 20x minus 12 over 15. And here again, the domain of this new function is all real numbers. So this function will be able to take any output from f of x and trace it back to its input. So our third example, we're going to consider the function f of x equals x plus 1 over x minus 2. So let's see if we can follow through our process again. Replace the f of x with a y equals x plus 1 over x minus 2. Interchange y and x. So where I see y, I write x, and wherever I see x, I write y. Y minus 1 over, y plus 1 over y minus 2. Here's where the work is involved. We need to solve this function for y. This is going to take a number of steps. First, I'm going to multiply by the LCD. Multiply both sides of the equation by the common denominator, which is y minus 2. We'll have x times y minus 2. And when we multiply the right side times y minus 2, the denominator will cancel. We'll have y plus 1. Our next step, I'm going to distribute x. We'll have x times y minus 2x equals y plus 1. As another step, I'm going to get all the y's on the same side. I'm going to get all the things that don't have a y on the same side. So I'm going to add 2x to both sides. I will subtract y from both sides. And we'll wind up with the expression. I'm going to come up here since I'm starting to run out of room. xy minus y on the left side of the equation because the 2x's cancel out. We'll have 2x plus 1 on the right side because the y and the minus y cancel out. We're almost done here. In order to get y by itself, my next step is going to be to factor. I'm going to factor a y that both of these terms have in common, factor it out, leaving x minus 1, because if I distribute y into this parentheses, I'll have x times y and a minus y. And as a final step, to isolate the y value, I'm going to divide both sides by the factor x minus 1. Divide both sides by x minus 1. So as my final step here, we will write the notation f inverse of x is equal to 2x plus 1 over x minus 1. Now, the domain of f inverse, notice that the domain of this function is all real numbers except x equals 1. I do not want x to equal 1. If I put a 1 into this function, I get 0 in the denominator. So it means I could trace any output of f of x back to its input except if the output is 1. Well, that seems strange. Why should I be able to trace every other output back to its input, but not the output x equals 1? Well, let's take a quick look at the graph of x plus 1 over x minus 2, and let's see if there's anything interesting about the output x equals 1. Let's see, I'll do a zoom square here. So here we go. It's drawing this function. Notice at x equals 2, we have a vertical asymptote. That's why x plus 2 is not in the domain of the original function. But notice also the output of 1 actually never happens. Let me add in the graph here of y equals 1. And notice that that is never an output that will come from the function f of x. There's a horizontal asymptote there at y equals 1. So turns out that's okay for our domain of the inverse to not be able to trace 1 back to an input, because there is no output of 1 that would ever trace back to any input. All right, we have one more example to take a look at. Our final example, f of x equals x squared plus 6. Only for x is greater than or equal to 0. So remember why we need that restriction on the domain of f of x. We've seen a quadratic function like this before. X squared plus 6 normally has the graph looking like a parabola with a y-intercept of 6. And this is not a one-to-one function. It fails the horizontal line test. If a function fails the horizontal line test, it doesn't have an inverse. So by restricting this to only x is greater than or equal to 0, we are only looking at that part of the function, which is a one-to-one function, and it passes the horizontal line test. Therefore, it can have an inverse. So let's find the inverse of this function. Follow our steps. Replace f of x with y. Y equals x squared plus 6. Step 2, interchange x and y. X equals y squared plus 6. Step 3, solve for y. Here's where we do most of our work. Let's subtract 6 from both sides. X minus 6 is equal to y squared. Final step, to isolate y, I need to take the square root of both sides. So y is now by itself equal to the square root of x minus 6. And of course, our goal was to find the inverse of the function. So finally, I'm going to write this with inverse notation. F inverse of x is equal to the square root of x minus 6. Now let's review domain again. The domain of a square root function is all x's that will keep the part under the square root greater than or equal to 0. X minus 6 must be greater than or equal to 0. Solving that means that x must be greater than or equal to positive 6. Simply add a 6 to both sides. So the domain x greater or equal to positive 6, it means it can only trace outputs back to inputs if those outputs were greater than or equal to 6. Well, remember our original function f of x? All of the outputs of f of x are greater than or equal to 6. Very smallest output I ever have is when x equals 0, I get 6. For any other number, I'm adding something to 6. So it's always greater than or equal to 6. So turns out this inverse function can trace any output of f of x back to its input.
So where is all this leading us? In the next couple of sections, we're going to be talking about exponential functions and the inverses of exponential functions. So we'll see an exponential function takes a particular base and raises it to all different kinds of possible powers. The input will be the power, and the output is going to be what we get when we raise the base to that power. The inverse of an exponential function works this in reverse. It takes numbers as input and finds a power of a particular base that will give us that number. We'll see more on this later. Thank you for watching this video, and we'll see you next time.